Hello, welcome to the second of 4 lectures on the geometry of scattering amplitudes. Today's lecture, I'd like to cover a lot of material, as usual, on the connection between these on-shell diagrams, recursion relations, and what they mean in a combinatorial picture. And the theme for today is really to touch many corners of the following duality. There's sets of connections, which is that planar diagrams that are undecorated are uniquely labelable by a permutation that we're going to define for you. And once you know those legs, the map from each of the external legs to another leg, as we'll see, this uniquely specifies a particular subvariety in the Grassmannian. So you can directly go from the permutation to the Grassmannian. And there's a one-to-one correspondence between each of these things and the particular on-shell function. So knowing the permutation allows you to forget about the function or the diagram altogether and just think about that. And there's an intrinsic sense in which the geometry inside the Grassmannian is also characterized by exactly the same permutation. And so in today's lecture, I want to talk about this web of combinatorial relations. That from the diagram, there's a permutation, and the permutation, you can construct a function and a diagram and construct this geometry. And similarly, from the geometry, you can also read off these permutations. And all of these things give you a combinatorial picture for these particular on-shell functions that are relevant for maximum supersymmetry in 4 dimensions. Yang-Mills theory. Yeah. So our picture, I'm going to start today's lecture actually by reviewing something we saw last time. And then we're going to discuss this web of dualities in a few different ways. We're going to go from these connections between the Grassmannian and these on-shell diagrams. We'll start by just thinking about the combinatorics, and then we'll flip it on its head, and we'll start from the geometry side, and we'll understand another road to this connection in the Grassmannian. We'll talk about how both of these things are basically describing 2 sides of the same story, and that this really unifies everything in planar maximum supersymmetry in a combinatorial way. More details can be found in this book here that I wrote with Nima Arkani-Ahmed, Freddie Kachazo, Yaroslav Trinka, Sasha Goncharov, and Sasha Postnikov. So, like I said, I want to start today with the where we left off, or something towards the end of the last lecture, which is this recursion relation. In particular, today, we're only going to be focused in on tree-level recursions. We're going to be looking for diagrams like this, where there's no further integrations to be done. So the class of diagrams where the n hat delta equals 0 are our focus for today. And you'll recall that we could stratify these, or we could organize these recursion relations according to the m of the amplitude, which is for gluonic amplitude is how many minus helicity gluons are involved. Remember, all the states are incoming. So that would tell you that it's that number m to the complementary number n minus m outgoing particles if they were all minus helicity gluons, say. But in a theory without arrows, like planar maximum supersymmetry, it's more easy to describe in terms of the colors of the vertices involved in the diagram. And we saw that that the recursion relations gave very concise formulas for non-trivial amplitudes, not beyond the Park-Taylor example. For example, this m equals 3 6-particle amplitude where you have 3 in and 3 out. Again, just flip the signs to make it 2 to some number if you'd like. And we remarked on the fact that there was not a unique representation of either the diagrams nor the terms that came out of the diagrams. That if you chose legs 1 and 6 to be the anchors of the recursion, you would get these 3 pictures, or actually you could get different pictures depending on how you recurse to these corners here. So you can get very different looking pictures. And you can also get different functions, because if you had picked legs 1 and 2 instead of 6 and 1, you would have gotten, who cares if they're different pictures, you would have gotten very different functions. It turns out no matter how you recurse the corners, you still get the same functions. So it's really just this first binary choice of which, or not binary, but which pair of legs did you pick to do the recursion on? for the 6-particle amplitude. And so there is no unique BCFW formula. But the other thing, and this is what I want to emphasize first and what we want to talk about first, is that these diagrams are related in very non-trivial ways. The fact that this on-shell diagram as a function is the same as this one with the legs rotated around is very surprising and very non-trivial and very annoying, in fact. And it's because of this fact that there are many, many diagrammatic ways of representing exactly the same function that people stopped drawing these pictures in the physics literature, because it's a very redundant way of talking about these functions, is to draw a diagram of it. Because once you draw a diagram, there's many, many inequivalent looking diagrams that give you exactly the same function. And I raised the question if there was a way to invariantly characterize the on-shell functions associated with these diagrams. And we'll see that the answer, in a moment, we'll see that the answer is yes. And in fact, it was known independently of the physics community by mathematicians. And if only we had read the right literature, we would have been substantial. We would have skipped over several years of confusion through the wilderness. So the combinatorial way of characterizing these diagrams, it starts from the recognition that there are two moves, and in fact only two moves, that connect different diagrams to each other that leave the function on the outside the same, unchanged. The first is that chains of same colored vertices can be arbitrarily rearranged. And this follows from from the on-shell condition and the momentum conservation. You can see that this just tells you that those four legs all have the same lambdas or proportional to the same lambda tildes. And you could thereby define a blue 4-particle vertex if you really wanted to, and make the graph bipartite, having two colors, having no same colored connections inside the graph. But the point is that you can rearrange the tree, and this will never change the function on the outside. So you can, so there's this is called the merge relation. And then the less trivial relation is called the square move, or this box relation, which is we already saw in the previous lecture, which is that the 4-particle tree amplitude can be represented by this picture or by that picture. And because both this picture, either this picture or that picture, represent the 4-particle tree amplitude, the Park-Taylor amplitude for 4 particles, it doesn't matter how you draw it. And so this also, inside of a diagram somewhere, can be changed and will not affect the function on the outside. It means the same thing inside the diagram. And these two moves are it. In fact, this is all that there are. And these generate extremely non-trivial connections between diagrams. And it turns out that the set of planar graphs, two-colored planar graphs that have that are related by these two sets of moves, also with white vertices merged, can be easily characterized by a very simple combinatorial label, which is a permutation defined as follows. You start on the outside of the graph, and you start at leg A. So say you start at leg 1, and then you go into the graph and you turn left at every white vertex. So 1 goes to 2, 2 goes to 3, and 3 goes to 1. And then you turn right at every blue vertex. So 1 goes to 3, 2 goes to 1, and 3 goes to 2. Now, it's very easy to see that these moves, these relations, equivalences between on-shell diagrams leave the permutation invariant. What's a lot less obvious, but is provable, that provided the two graphs have the same number of faces, that if they have the same permutation label, they are related by moves. And that means that these permutations uniquely characterize that on-shell function and uniquely label that equivalence class. And it's also, just to be clear that we're talking about a permutation, you can easily see that, that every path has to come out somewhere starting. In particular, you can see this because changing the color of the graph, if you just change every vertex from blue to white and vice versa, reverses all of the arrows throughout these flows. And so every path that comes in has to come out too. So you know that you're going to land somewhere on the outside of the graph. You can't have a closed loop, can't terminate somewhere inside spiral around forever, at least as a planar graph. And so this gives you a unique label. And this is how, remember that I told you that just a few slides ago, that this on-shelf, the on-shelf function attached to this diagram and the one for this diagram were almost the same. I mean, up to a rotation of labels. And so more concretely, the claim is that this on-shelf function and this on-shelf function are related by moves, by equivalence relations. And if you believe me that the permutation, it's clear the permutation is left invariant by the moves, but if you believe the converse, then all we need to do is check the permutation labels for the two different graphs. So in each case, leg 1 follow the path, and at leg 3, 2 goes to 5, 3 goes to 6, 4 goes to 1, 5 goes to 2, and 6 goes to 4. And for reasons that will that are more important for the general toolbox of this game, I'm decided to boldface these things that go to something less than themselves. This, of course, depends on where you started to label. It's cyclically ordered, but where you chose to start with leg 1, we're just going to conventionally declare that any leg that goes to something less than itself, we're going to add n to its image. So these are called decorated permutations and not just simply permutations. So they're maps from 1 through n up to 1 through 2n in general. And if you mod out by n, you get a normal permutation. But this allows us, at the moment, it's just a stupid convention that I'm going to enforce on us. But we'll see why it helps us later on, because it turns out that there's it's an important part of the toolbox, but for reasons that will become clearer later, when a leg gets mapped to itself, it's important to distinguish it, whether it goes directly to itself or whether it goes all the way around to itself. And that's where the decoration really matters, where you can't just mod out by n, because it matters whether something goes directly to itself or to itself plus n. But anyway, at the moment, for every diagram we get from recursion relations, this never happens. You don't have things that are self-identified, so don't worry about that too much. Right now, it's mostly a convention. So notice that the merge and square moves leave the number of faces on an on-shell diagram invariant. And that means that, oh, so you might wonder immediately, clearly there's a finite number of permutations, but I can draw diagrams forever. So how could there possibly be a finite number of on-shell functions? And the first point is that neither of these moves change the number of faces of a diagram. And there is a relation. It's not an equivalence. It's a semi-equivalence, or it's something like I'll make it clear what I mean by this. There's a notion of having a diagram be reduced and not reduced. And reduction happens through bubble deletion, which is if you have this little bubble inside of a diagram, you can delete it. It does not give you the same on-shell function, but it gives you just a trivial prefactor in front of it. So it leaves behind just a d alpha over alpha on the on-shell function. So it gives you a very simple volume form on it. And so up to bubbles, and it does change the permutation, by the way. So, so the number of reduced on-shell diagrams is characterized by permutations. And then there's an infinite tower of plus bubbles that does not really affect the on-shell function. It just adds a d alpha over alpha in kind of a trivial way. This seems pretty trivial and pretty stupid, but it plays a big role in the loop level recursion, as we talked about last time, or at least briefly. For example, in the 4-particle amplitude, it was important that it had 4 extra integrals to do, and all of those 4 extra integrals can be identified with bubbles inside that diagram. So non-reduced diagrams. Okay. So one other thing is, I mentioned this technology that it was very useful to relate diagrams to each other by adding BCFW bridges. And if you think about this in terms of permutations, this acts in a very simple way. In fact, a way that becomes extremely powerful once we follow it to its conclusion. So imagine we had an on-shell diagram. We saw as a function that adding a BCFW bridge just shifts the momenta of A and B into this core. And it and it adds one new degree of freedom, alpha, inside the integral. Acting on the permutation, this acts very simply. It just transposes the images of the legs A and B. So if A went to sigma of A, now A goes to where sigma B used to be. So the images of two legs get transposed when you add a bridge. And this is just kind of a cute observation until you realize that you can actually read it in reverse. That you can take an on-shell diagram labeled by some permutation, and you can remove a bridge and get to a simpler on-shell diagram where the images have been transposed. And this actually leads to an extremely powerful and efficient way of representing on-shell functions and even generating diagrams. And the way this works in practice, I will illustrate by example, and I'll ask you to do it in your homework too. But the basic idea is that by sequentially, if I handed you a label and not the diagram, you could deconstruct that permutation into a series of transpositions to the identity permutation. And what you would do, which you would be doing, is generating that function iteratively by a sequence of very simple moves. And this sequence of very simple moves also generates a diagram for you that has that label. So this is one way of connecting everything together. And there are many ways of decomposing a permutation into adjacent or into transpositions. But what I want to describe is one specific way, and I want to be very clear about the rules here. The rule is you take this permutation, and the rule is if you want to go to a lower one, you transpose the first pair of legs whose images are ordered. That's it. And you skip over anything that is that maps to itself or itself plus n. So you can skip over things. Right now, there's nothing to skip over. And so the rule is you remove you take the first transposition where the images are ordered. And so suppose that I emailed you this permutation, 3, 5, 7, 6, 7, 8, 10. Remember 10 means 4 mod 6. And I would like to show you how this bridge decomposition will construct a representative diagram and a representative function for you. So this is what we're supposed to have in mind, that we have some kind of blob. We don't know what it is. We don't know what it looks like yet. All we know is that leg 1 goes in and then it comes back out at 3. So that's this transposition, this permutation. So we follow this rule. We take the first, it's called the lexicographic bridge decomposition. There are other strategies you can pick. This one has some nice properties. It's not especially canonical, but it does have some nice properties. So the first pair of legs whose images are ordered is 1 and 2. So we're going to imagine that this diagram that you had in mind that you emailed me is actually something like a bridge on a simpler diagram. And the function that we have that we care about is d alpha over alpha times some simpler function where the legs get shifted, right? And now we look at this and we find the first pair of images that are ordered. And what we see is that 2 goes to 3 and 3 goes to 6. Neither of them are the identity, so we are going to transpose 2 and 3. So now this graph is something simpler on this thing. And you can keep track of the permutations and see that the permutation label for F2 is 5, 6, 3, 7, 8, 10. But you will notice that now leg 3 goes to itself. We're going to skip over it from now on. Why? Because you can see that relative to this graph here, whatever it is, 3 is just kind of hanging out. It doesn't play any more roles because it just goes directly to itself. Everything is skipped over on 3. So, so we can skip over adjacent legs. So we look at this and we see, oh, well, 1 and 2 have ordered images. So we're going to transpose that. And now they're not ordered anymore, so we can't do 1 and 2 again. But we can do 2 and 4. Those are ordered. So we get that. And we keep following this procedure all the way down. We skip over things that are mapped to themselves under the identity or themselves plus n. And what we land on is a very simple, something that is a decoration of the identity. So everything goes to itself or itself plus n here. And once we're there, we're done. because now we have a graph, and it is very easy to verify that this graph, I mean, just it's trivial to prove that this graph will have the permutation label that we started with. And at this point now, there's no graph below us. It's an empty graph that's left. Okay, and we have a representative of the function where it's all a bunch of shifts, of BCFW shifts on something that should be kind of trivial. But what is this F8 down here? It's the on-shell function labeled by this identity permutation. Well, one way to see what we're talking about here is to literally remove all the bridges. So we can sequentially remove all of the bridges. And what we land on is a graph that is empty, where there's everything, all the momenta flow in and stop. If you think about this as momentum as constraints on the external momenta, it tells you that the momenta flowing into this diagram are all zero. They all have to be zero. And now we can see why this decoration was useful, because some legs go to themselves and some legs go to themselves plus n. So 3 goes to itself and 5 and 6 do, but 1, 2, and 4 go to themselves plus n. And what you can see is that it's now distinguished by whether it's white or blue, and that tells you whether it's a constraint on the lambdas or a constraint on the lambda tildes. So to have the momenta 0, you can have either lambda equals 0 or lambda tilde equals 0. And this distinction is now represented by these things. So what is this silly on-shell function where everything comes in? Well, if we want to make the lambda tildes of particle 1s, 2, and 4 vanish, and the lambdas of particles 3, 5, and 6 vanish, basically the function that we have here is just a bunch of delta functions. Forget about this eta tilde. Again, we're not really talking too much about supersymmetry, but it's there. And so we have 3 delta functions for lambda tildes and 3 for lambdas. This can be encoded a little bit more prettily as a matrix by introducing a matrix C. So C is something with the identity in columns 1, 2, and 4, and zeros everywhere else. And it has an orthogonal complement with identity in columns 3, 5, and 6, and zeros everywhere else. And so instead of just writing these 6 delta functions saying that either lambda or lambda tilde of every particle is 0, so it's 2 delta functions per particle, instead of writing that, we can write it this way, which I hope is at least reminiscent of what we had. Notice that the delta functions will never change. Okay. And so you always have 2n delta functions, 2 per particle, whether it's and the only distinction is whether it involves lambdas or involves lambda tildes. And of course, the 2n delta functions always includes an overall momentum conservation, which in this case is a little trivial because these constraints tell you that all the momenta are 0. So obviously that conserves momentum. Anyway, when you work out how this adding a bridge affects this matrix in terms of shifting the lambdas and lambda tildes, what you see is that the matrix shifts in a very simple way. Adding a bridge between legs 4 and 6, which is, remember, white to blue, shifts column 6 by this variable times what column 4 used to be. So what column 6 used to be maps to itself plus alpha 8 in this case times column 4. So we had originally column 0 plus alpha 8 times this column. So the new matrix, so this would be F7. F7 has this matrix attached to it. So it's d alpha 8 over alpha 8, d log alpha 8 if you'd like, times this with this matrix now. And then as we add another bridge, we shift column 4 by column 2. So column 2 was 0, 1, 0. We add that to column 4 and we get that. And we keep going. And thereby we build up this big matrix. And it depends on 8 internal degrees of freedom. Now, you might be worried about these internal weird little things. And also, what is this contour of integration? But the reason why you shouldn't care or you shouldn't worry about it right now is that, again, we always have these same numbers of delta functions here. That never changes. None of the delta function structure never changed in this whole process. The only thing that changed was the number of the dimension of the form. And when we got to the very top, we had 8 internal, bridge parameters, and we have 2 times 6 is 12 delta functions. of which 4 are momentum conservation. And that means that we have 12 minus 4, 8 delta functions net. And we can use those 8 delta functions to completely isolate all of these alphas. So there are no more alphas left. This is using these delta functions to do the integral completely locks all of the 8 alphas, and we are left over with a matrix that only depends on lambda and lambda tildes. So we have constructed the matrix. This turns out to be extremely powerful. So we've actually done several things here. By decomposing this permutation into adjacent transpositions, we've constructed a matrix, which is encoding, we'll see how that works later, as a 3-plane in 6 dimensions. We've found a functional form of the function that we care about. And we also constructed a graph. We did all of that at once. And we could actually go up a little bit higher and get to a slightly more general permutation, which would be to, which instead of like F1 or F0, we could go to like F minus 1, where we shift columns C1 by C6. So we add one more bridge to the picture. And then what we get is we get a generic configuration. Why am I saying it's generic? So you might want to ask yourself what the dimension of the space of 3 planes in 6 dimensions are. What is the dimension of the Grassmannian? Where the Grassmannian is coming in is not so clear right now. I admit that. But the space of 3 planes in 6 dimensions is a space of 3 by 6 matrices modulo GL3, which is 6 times 3-dimensional minus 3 squared. It's equal to 9. So in fact, you can go one level higher and you can get a generic configuration. And what we can see is that the columns, if we look at this column space, when alpha 0 goes to 0, we land with a very special kind of configuration where this determinant, 3 by 3 determinant, is 0. What this means geometrically is that if you look at the first 3 columns of this matrix, they span a 2-dimensional space, not a 3-dimensional space. So whereas if we added this extra 1, they would span a 3-dimensional space. They'd all be generic. So we can already see that there's some sort of connection. As we sequentially remove or set the parameters to 0, we get to these much more special configurations, where at the very bottom, we land on a configuration that only has 3 non-zero columns, 1, 2, and 3. And so if we now walk back up the bridge, or the sequence of bridges, what we see is that we're getting these kinds of configurations of columns that describe, a polygon in the plane, in the projective plane. I'm drawing these projectively, but it doesn't really matter very much. Okay. Oh, I have to go the other way. Yeah. Okay. So there's this whole connection in both directions. We can remove the things, and we're exploring configurations of points in P2, or columns, spans of 3 vectors in C3. It's not really projective because we can set the columns to 0 if we'd like. And what we find is that this kind of configuration, where we actually go back up to the generic configuration, this wedge product of all these d logs, it turns out that as a differential form, this has another way of representing it. In fact, it is the volume form on G36 times the product of all the consecutive minors of this matrix. And this form should be very suggestive and very should hint at something like Park-Taylor. Instead of 2 by 2 things, it's 3 by 3 minors. So this means this thing 1, 2, 3 in parentheses means the determinant of columns 1, 2, and 3. 2, 3, 4 means the determinant of 2, 3, and 4, etc. And this is the top dimensional form. So the general on-shell diagram, and this is a particular top dimensional form on the space of 3 planes in 6 dimensions. So this is one way to kind of understand this, but I want to emphasize that at no point do we talk about positivity, and at no point other than that, when all the alphas are positive here, it turns out that that all the consecutive minors of this matrix are positive. That means that the areas of the polygon, so it is a convex polygon, but that's not something we're going to talk about too much here. And in general, it turns out that the sequence of bridges starting from a generic permutation all the way down to a 0-dimensional cell gives you this. And so this is one way of connecting this, what's called the positroid stratification of the Grassmannian, is as somehow residues or something like that of this volume form. And you look at this and it's products of k by k minors in the denominator, and products of k by k minors are usually kth degree polynomials in the variables. So it is not at all obvious that there are simple poles, let alone that there's a sequence of simple poles that will take you all the way to a 0-dimensional cell. And this kind of connection and subtlety about the pole structures is a very interesting one. Oh, one upshot that I'd like to emphasize immediately, or just, but kind of in passing, is that this form, although this volume form changes from theory to theory, in maximal supergravity, it looks very different, and in pure Yang mills, it's different still. This structure is completely generic. And in fact, the variety has nothing to do with the theory. So as long as you have blue and white vertices, the particular cell, the particular C alpha that you get is the same regardless of what particles you have inside the diagram, regardless of what theory you're in. Only thing that matters is the volume form. So the subspaces, C alphas, that, so as you move around in alphas, you move around in particular 3x6 matrices. Those change. So the subspaces are all the same. They don't depend on the theory. They depend on the diagram alone, the undecorated diagram alone. The volume form definitely depends on the theory. But importantly, if you look at this and you say, because of the delta functions, you can take a volume preserving diffeomorphism among the alphas, so a functional map, rational functional map or polynomial map even, a diffeomorphism among the alphas, a generic diffeomorphism that preserves this volume form. And you can, every such diffeomorphism, you can then translate into through the delta functions into an active transformation of the lambdas and lambda tildes. And when you ask, what are the volume preserving diffeomorphisms among the alphas, it turns out the answer is it corresponds to Yangian transformations. And so the Yangian, this infinite dimensional symmetry of maximum supersymmetry in the planar limit, which was discovered as a property of these diagrams, is fairly trivial from this point of view. It is just the space of diffeomorphisms. The fact that this thing has an infinite dimensional symmetry algebra is not surprising. It might be a little surprising that you can preserve all diagrams, which is not generally known for non-planar, etc. But this is a property of on-shell diagrams. It doesn't have very much to do. The fact that we have a name for it and we call it the Yangian in the planar case of maximum supersymmetry doesn't feel that special. Okay, so another road to this is to think about, say, the singularity structure of the amplitudes that we've already seen, some of them. This is another way that we would have discovered this Grassmannian connection. And take, for example, the Park-Taylor amplitude for 4 particles, say. So this is a very simple thing. This was the one that was guessed. I mean, it wasn't the one they guessed was the 6th particle. Well, they guessed all of them. But it has this simple sequence of factors in the denominator, little determinants of the matrix of lambdas. So remember, we have this 2x4 matrix lambda. We can think about it as representing a 2-plane in 4 dimensions, so an element of the Grassmannian if we'd like. And what does it mean to sit on one of these poles or to take a residue of this form? And one thing that we can see is that when we think about the columns here, especially because we can rescale them uniformly, it's kind of more natural to think about them in projective space. And why not think about them in real projective space, which is just a circle. RP1 is a circle. So because the only first order poles, the codimension 1 residues you can take, involve consecutive pairs of spinors. So it's 1, 2, and then 2, 3, 3, 4, and 4, 1. You can think about it as having points arranged consecutively on a circle. And the geometry of configurations of points on a circle is in fact one-to-one correspondence with the iterated factorization channels of this amplitude. And we can work this out actually in full gory detail. So you can look at what are the codimension 1 singularities? Well, any one of these, maybe lambda 3 and lambda 4 become proportional. When that happens, the matrix looks like this. This minor is 0, and you have a lower dimensional cell. You can also have, say, lambda 1 and lambda 2 become proportional, et cetera. So you have 4 codimension 1 configurations, these solid triangles. And they're glued together along lower dimensional configurations. Anyway, I'm going to spare you the details, but if you flesh out all of the possible factorizations all the way down to the 0 dimensional cells, where you just have 2 points and the other things are 0, you get this very interesting shape with a very interesting boundary structure. And it's interesting that this predates our understanding of the positive Grassmannian by a long shot. And this picture was taken by this paper by Galfond and McPherson in 1982, where they talked about generalizations of the dilogarithm in this context. But they fully iterated this entire boundary structure of what we would call the Park-Taylor amplitude back then in 1982. I'm not sure how illuminating that is, but this is the kind of general structure we'd like to better understand. So another way that we could have really led ourselves to this Grassmannian was by just starting at the Park-Taylor amplitude. Remember, so this is what the amplitude is for 2 to some number of particles, where you have just these little lambda minors down here. And we'd like to somehow guess a generalization of this formula for some other number m, say, of negative helicity. So instead of m equals 2, we'd like to look at m equals something else, m equals 3 or 4 or something. And in terms of this kind of Grassmannian picture, we have this 2 by n matrix lambda, and it appears in these 2 places here in the delta functions. And we remember that this momentum conservation is really this geometric constraint, that there's a 2-plane lambda and a 2-plane lambda tilde, and they are orthogonal. They have to expand different spaces. In order to, thinking about what the helicity means in this language makes it clear that if this was a 2 by n matrix lambda, that in order for, if m were to be some other number, you'd have to get an m by n matrix. Some C matrix like this, something like that. Maybe we could call it capital lambda, but then it would just be a little confusing. And thinking about how little group works and whatnot, there's really more or less a unique guess that you would make, which is that maybe the m equals m generalization of Park-Taylor would be, instead of having 2 by 2 minors, you have 3 by 3 minors or 4 by 4 minors, and it looks like this. This is a very natural guess, and we will see in a little bit that in fact it's right somewhat. And to understand why it's right somewhat and not just dead on correct, it's useful to consider a couple cases and to think about what this could possibly mean here. So the first point is how does lambda go into this situation, or how does lambda get generalized? The first point is that if we had to shift lambda, this 2 by n matrix, with some bigger matrix, and it's actually, in order for this set of constraints to include momentum conservation, it's important that this m plane contain lambda as some subspace of it. So the picture is that we have an m plane, m rows of some m by n matrix C, and it has to contain inside of it lambda, or else this thing won't include the delta functions, the momentum conservation there. So we must insist that C contains lambda. And in terms of these like dot product-y things, the way I'm going to write that constraint is a little bit ugly, and I apologize for it. But it is to say that lambda is orthogonal to the orthogonal complement of C. That is the way to say that C contains lambda, right? So if C has a n minus m plane complement, it's all the space not spanned by C. And we have to say that lambda is orthogonal to that. This constraint is equivalent to the constraint that C contains lambda. All right, so we're led to a form like this. The eta stuff, again, just ignore it if you want. Okay, so let's consider the first case where m is not equal to 2, and it's also not equal to n minus 2, which is the case of m equals 3 for 6 particles, that first case. And we'd like to ask, is this sensible? I mean, is this the kind of amplitude that we'd like? Is this a single term formula? We saw BCFW gave us 3 terms. But is there any sense in which this kind of a statement is true? And the first point that we have to notice is that the right-hand side doesn't exactly make sense fully yet. And the reason is because we can view this by just thinking about how many degrees of freedom we have inside the Grassmannian of 3 planes in 6 dimensions. Again, it's 3 times 6, 18, minus 9, minus GL3. So 3 by 3, so general 3 by 3 matrices. So 18 minus 9 equals 9 degrees of freedom. So that is how many degrees of freedom. That is the dimension of 3 planes in 6 dimensions. And we can see is that the number of constraints we have here again is 3 times 2 and plus 3 times 2. So it's 8 constraints, and that means 8 constraints plus momentum conservation. That means that even after you've imposed all of these delta functions available, you have 1 internal degree of freedom, 1 left over. And so as a current right-hand side guess that you might write down for the 6-particle amplitude, this has an internal degree of freedom attached to it. And I don't know what that internal degree of freedom is. I mean, we could solve the delta functions explicitly and write down a formula that involves this internal degree of freedom, but we can see it more explicitly kind of this way. Let's just suppose that so we can solve the first set of delta, or these delta functions, say that C contains lambda. We can solve that kind of trivially by just putting lambda in the bottom, in this row here. I probably didn't want to draw on the slide, but I can just put lambdas in the top 2 rows. And then we have these things left. And it looks like we have 6 numbers we don't have fixed, but we also have a GL3. And so there's really just 1 degree of freedom shared among all of these things. The details really don't matter. The point is that now we've imposed all of these. C dot lambda tilde is trivial for the top row, because the top 2 rows, because that's momentum conservation. And then we have this last set of constraints here, which is that the bottom row is orthogonal to lambda tilde. Okay. The point is that this is a 1-dimensional space of solutions. And in particular, we can think about these minors that appeared here, minor 1, 2, 3, and 2, 3, 2, 3, 4, and all of the consecutive minors, as depending on this unspecified final degree of freedom, say tau. And this is what the form looks like, tau. And we have simple poles. We have a pole when minor 1, 2, 3 equals 0. Okay, and what does the answer look like there? Well, in terms of a generic configuration, it's not quite generic, because the first, when minor 1, 2, 3 equals 0, the first 3 columns only span a 2-dimensional space. They're lower. And that means that, said more concretely, that 3 is in the span of 1 and 2, okay? Or 1 is in the span of 2 and 3. It doesn't make any difference. So we have a configuration of not 6 generic points, but 6 points subject to 1 constraint, that minor 1, 2, 3, or the triangle spanned by 1, 2, and 3, if we think about this projectively, has no area, or that they're collinear. So we have this configuration, but we have 5 other configurations. We have a place where minor 2, 3, 4 equals 0, etc. We have 6 different places, simple poles in this form. And about each one of these simple poles, we have a very simple configuration to talk about. And if, for example, if we take this particular one, this residue, it is now a specific function. We've now eliminated, if we do the contour integral around this equals 0, we get a specific, now there's no more internal degrees of freedom, and the residue about that is just evaluate everything else at that point. And this is the on-shell function in question. And it turns out that this thing, for example, if you could take this, the alternating helicity amplitude, if you'd like, or component of it, and it turns out that this thing here is exactly one of the terms that occurs in BCFW. So what this is telling us is that if with this guess of, can you just take, is it true that, so the 3 terms that we had in BCFW is the residue around minor 1 equals 0, the residue around minor 3 equals 0, plus the residue around minor 5 equals 0. But the other formula we could have gotten, remember I told you there was very different looking formulas, could have been 2, 4, and 6. And now we see that the equivalence between this recursion relation and that recursion relation is just a homological, it's just Cauchy's theorem up to a sign. We're not being a little ambiguous about the sign here, but up to a sign, the equivalence between these two representations of the amplitude are just a homological identity. It's taking the space and carving it up in two different ways. And so this is what led to the original guess in the Grassmannian correspondence by Cacciazzo and Arcani-Med and Chung and Kaplan, was this kind of general guess. Is the amplitude for m incoming particles and n minus n outgoing particles this generalization of Park-Taylor? And the answer is yes, kind of. That there exists a contour prescription that encloses some number of poles inside this differential form where the answer is yes. And the connection between residues of this form and on-shell diagrams took a lot longer to work out, but that's what I want to talk about here. So it was later proved, shortly after this kind of connection, this kind of ansatz was made for BCFW terms, it was proven that the residues of this thing are in one-to-one correspondence with on-shell functions in n equals 4. So that means that the problem of enumerating on-shell functions or drawing them or whatever is equivalent to the mathematical problem of take this differential form on the Grassmannian and what are all of its residues? What are the possible contours of integration? How would they be classified? And what relations, how are they identified with on-shell diagrams? And what relations do they satisfy? All of these questions were open about 15 years ago, or no, it's not that old, 13 years ago or so. And it took us a few years to kind of get to it. And in fact, to be honest, we didn't get to the answer. The answer was provided to us by Pierre Deletion. We got pretty close to it. And but the short version is that we basically asked him this question. We have this differential form in the Grassmannian, and how would you characterize and describe the possible contours of integration of L and M of this space, of this differential form inside this, in this big space called the Grassmannian? And Deletion's first insight was that clearly the only data that you could care about, because it's GLK invariant, it can't even be in terms of minors. It could be ratios of minors, I guess, but much more importantly, the most unambiguously GLK invariant data to describe a K-plane in n dimensions or an M-plane in n dimensions would be the ranks spanned by subsets of columns. That kind of data is called matroid data. But the important thing about this is that because these are consecutive sets of minors, are the only things we care about, it's natural to think about only consecutive chains. And so Pierre first suggested that we think about this big giant list of data that is clearly redundant and to describe these residues. And it's one of these beautiful things where you look at it exactly one example and you understand everything. So first, let's just use A up to B to denote the rank of the space spanned by the columns A up to B. And we can write this in a grid. So we can start with all the chains of columns, 1 up to 1, 1 up to 2, blah, blah, blah. And we can list all these ranks. And in fact, there's no reason why we can't keep going all the way up to, we can even go on forever if we want, keep going around cyclically. And we can generate this big, huge list of matrix ranks. And clearly this is all GLK invariant data. And it also is only data that is sensitive to consecutive constraints. Okay, for any generic configuration up at the top, everything up here, so anytime you look at K consecutive columns, you span a space of rank K. In fact, we can even continue this diagram up diagonally forever by just using cyclicity in our labelings. And we can even go down below this diagonal by saying that if A goes to the span of columns from A to A minus 1, which is an empty set of columns, that should have rank 0. So we can put zeros along the diagonal here. And so the rank span from columns from 1 up to 1 is either 1 or 0. This is either 1 or 0, etc. So everything along this diagonal is either 1 or 0. And as you go up in the column, you are monotonically increasing. And as you go left from the diagonal, you are also monotonically increasing. And it turns out that all you need to do is look at this data once in one example, and you will understand everything. So let me illustrate that or prove this too. So consider a generic configuration of in G4-8. So of points in 4 dimensions. There are 8 points in 4 dimensions. And now there's nothing really about positivity. It's really just about consecutivity. So we look at this arrangement of ranks, and this is a little impossible to make sense of. I mean, I don't know, my eyes can't see it. So I'm going to color it to illustrate it. So you can see that the ranks, if you take 1 column, it's rank 1. 2 columns, you have to get rank 2. So it's a very trivial kind of rank table. Clearly, this is a very redundant description of things. But all we need to do is look at what happens in one example, and we will understand everything. So the first is that, imagine we took minor 6, 7, 8, 1, and we set it to 0. What does that mean geometrically? It means that the space, the columns 6, 7, 8, 1, which used to be which were rank 4 in general, dropped in rank to rank 3. So what would happen is that in this table of matrix ranks of columns, we get a 3 inside here. That's what changed when we did this move. But now what if we took 0.3 and we put it onto the plane 1, 2, 3, 4? Well, again, this little entry would turn green, okay? And we could take a bunch of iterated residues and see what happens. And iterative just means that we're going to look at constraints among consecutive groups. So for example, we can say that 0.5 is both on the plane 4, 5, 6, 7 and 1, 2, 3, 4 by moving it up to that point. And we can see that this table of columns is kind of, changes in a very interesting and specific kind of way. And even without studying an example, I think you would be able to realize that the entire table, by just the monotonicity in both the positive direction and in this direction, is entirely dictated by n points, n dots, which are the corners where things, so if you look at this list of, all these colors here, all you need to do is know these extremal corners. There's one there, there's one there, there's one there, there's one there, there's one there. And that describes, in fact, a permutation for you. To understand that, you can see that the dots here are connecting a point here to something over there. And it's a cyclic permutation, and everything goes to itself plus something. It goes to something greater than itself. And this permutation is very easy to describe. Sigma, so this dot means the permutation goes from 1 to 5. The next one, 2 goes to 4, 3 goes to 8. Anyway, if I told you this permutation, I claim that you could easily reconstruct this whole table of matrix of ranks of consecutive columns. So there's a unique configuration attached to each one of these things. Also notice this decoration business is actually distinct here. It means something different for something to go to itself, which is that that the rank of the column is 0 versus going to itself plus n is slightly different. And so the geometric meaning of this permutation is very easy to define. For every column A, there is a unique nearest column, so a minimum column B, beyond A, such that A is inside the span of A plus 1 up to B. So, for example, if A is actually empty, then it's in the empty span, so A goes to itself. If A and B are proportional to each other as columns, so they span a one-dimensional space, then A is in the span of A plus 1, and so A goes to A plus 1, etc. And you can now see this more clearly here. So 1 is not proportional to 2, so 1 does not go to 2. It's also not along the line 2, 3. It's also not along the line 2, 3, 4. However, it is on the plane 2, 3, 4, 5. And that means that the nearest element beyond 1 that in which column 1 is spanned is the set 2 through 5. So 1 goes to 5. Similarly, 2 is not spanned by column 3, but it is spanned by the line 3, 4. So column 3 and column 4 taken together will allow column 2 is inside that space. So 2 goes to 4, etc. Now, thinking about this geometrically actually gives us a lot more information and in a lot more transparent kind of way. For example, you can think about what is the dimension, how many degrees of freedom do you need to specify this configuration? Well, for example, if 1 is inside this plane, then it requires a rank 3 space, 2, 4, and 5, or 2, 3, this is a 3-dimensional space. I'm drawing it projectively. So the rank of that dot, basically, tells you that you need 3 degrees of freedom to encode column 1. And you need 2 degrees of freedom to encode column 2, which is, it's 3 times something and 4 times something. Those 2 degrees of freedom are there. So the number of crossings in this table of ranks, or called a juggling pattern, something, tells you how many degrees of freedom you need to specify this configuration. And in particular, the dimension of that configuration is just the rank of A up to its permutation image. And that overcounts the rank by k squared. So because there's still the overall GLK that. And so this immediately tells you something, and that these dots count the dimension of the space. And it also tells you what it means to go down in dimension by 1 in terms of these permutations. It means you have to do a transposition that deletes a dot. And so in particular, you could say that the boundary of a configuration are all those configurations labeled by a transposition such that the dimension drops by 1. And this is very easy to understand. If you have any A and B, not just adjacent ones, but any one, we can, if we transpose the images of A and B and we delete 1 dot, we get a configuration whose dimension has been dropped by 1. And we can think about that as being on the boundary of the original configuration. Notice that it does not matter if there's more dots sitting around, like maybe the dots move around. Like if there's another permutation that crosses here, it's okay. Or if it goes from here to somewhere out, it's also okay. But it's forbidden. But what you can't have is a permutation that goes from something between A and B and whose image is between the images of A and B. If you have that and you do the transposition, you get a configuration with dimension 3 less, not 1. And so you can look at a permutation, you can transpose anything you'd like, and you will get, as long as the images are ordered, so you need, in order for you to delete a dot, you need the image of A to be less than the image of B, with cyclic labeling understood. And as long as it lowers the dimension of the configuration by 1, you get a boundary configuration. And this actually enumerates not only all the configurations inside, all the residues of ln m, in the language of the previous couple slides ago, but it tells you how many there are and how they can get encoded. So the rule is that if as long as the images of A and B, the image of A is less than the image of B, and B is greater than A, and as long as there's no path that goes from between A and B into between the images of A and B, then it's a boundary. And so we can really, and just as for permutation labeling's on-shell diagram, we can actually decompose these permutations into adjacent transpositions in exactly the same way. And what we see is that we iteratively lose dimension until we get down to a trivial configuration, which in this case is one where there's only k squared dots, or 4 squared dots in this case here. And we have some 0 columns, which go to like 4 goes to 4 and 5 goes to 5. But then we have other kinds of columns like 6 goes to 6, or 14 is 6 plus 8. And so the same kind of build-up sequence that we get to talk about these configurations, we can play the same game. And the fact that the BCFW bridge construction generates both these configurations and the functions and the geometries all at once tells you that the labels that describe the geometry are the same labels as what describes this. So I hope, I mean, this has been actually I'm not completely out of time yet, but the point of this lecture was to illustrate all of the different arrows inside of this web of correspondences. That between on-shelf diagrams, you can there's a permutation label, which also describes the geometry of this matrix encoded the same way. And from the permutation, you can construct the function, you can construct the geometry, you can even construct a representative diagram. And so it is now true that you do not need to draw diagrams or even write functions down. The functions are all derivative. All you need to do is email me a permutation and I will know what you're talking about. And I will know it invariantly. All of the BCFW recursion, for example, gets mapped into just a simple statement about permutations weaving into each other. And there's a lot more details to talk about. Oh, and these things are in one-to-one correspondence with particular contours of integration on this particularly nice Park-Taylor-like form on a top-dimensional form on the Grassmannian. More details can be found in this book, where we talk about this in a lot more, a lot greater depth. In the next lecture, I'm going to talk about how this applies to non-planar theories, and then in the final lecture, I will switch modes entirely and do some computer programming for you. So thank you very much. Have fun with the homework.